colloquium of the semester. It's a pleasure to introduce Scott Aaronson. Scott finished his PhD in Berkeley in 2004. He then spent years as a postdoc at the Institute for Advanced Study in Princeton, and then 2 years more at the University of Waterloo. He's been a professor at MIT for 9 years until 2016, and then he moved to the University of Texas at Austin. And today he's going to tell us about shadow tomography of quantum states.
Okay. Well, thanks a lot. It's always great to be here at the Technion and visit old friends and new. So I want to tell you about some recent work which continues a theme that I've been interested in for at least 13 or 14 years, about how can we sort of approximately reconstruct the quantum state and sort of cope with the fact that quantum states in some sense are these exponentially large objects. Okay, so let me just start with an observation that I have to spend a lot of time on when I give this talk to computer scientists. But because this is a physics colloquium, I can go very quickly through this. Measurements in quantum mechanics are destructive. Okay, so if we think of just a single spin 1/2 particle, or as I would call it, a single qubit, in some sense, already there are infinitely many bits of classical information, right? And a qubit is alpha 0 plus beta 1, where alpha and beta are complex numbers. Right? And quantum mechanics puts no restriction whatsoever on the precision that these complex numbers could have. So the binary expansion of alpha, might contain, the complete works of Shakespeare and, all the wisdom of the universe somewhere in it. Okay, but somehow it's not accessible to us. Okay, if you were to measure this qubit and ask it whether it's 0 or 1, well then it will just tell you that it's 0 with probability absolute value of alpha squared, and 1 with probability absolute value of beta squared. And then whichever outcome it picks, it will stick with that one forevermore. Okay, and so in some sense we only get out one bit of information. Okay, so now this destructive nature of measurement in quantum mechanics is what opens up many of the cryptographic possibilities of quantum information. Okay, so it can be very useful. For example, quantum key distribution, which was just in this past year demonstrated by a group in China, across a distance of thousands of miles, to and from a communication satellite. This relies essentially on the fact that if an eavesdropper tried to measure the qubits going through the channel to learn about them, then the eavesdropper would destroy the qubits, okay, disturb them. And that fact could be detected by the legitimate parties. There's also something I've been personally very interested in, is the possibility of quantum money, okay, which would be quantum states that could be verified by anyone as sort of legitimate money, but which would be either impossible or infeasible to make copies of. Okay, again, if you try to learn, what is this money state to make more copies of it, not only will you not learn, but you'll even destroy the money that you had. Okay, I don't know whether quantum money will become practical, and if so, whether it will become worth $10,000 per quantum coin, the way that Bitcoin has. Okay, but we will actually talk more about quantum money later in this talk, because it was one of the main motivating examples for the kinds of results that I'll tell you about.
How do you tax it?
How do you tax it? I will leave that as a problem for others. What?
That's an advantage of quantum money.
Yeah, right. One could just as well ask how do you tax Bitcoin, right? The whole motivating point of it was that it's supposed to be independent of governments, right? You know, of course, once anything becomes valuable enough, governments will get in on it. So that's not really a stable situation, you could say. All right, but back to quantum mechanics. You know, now, not only are measurements destructive, but if we consider entangled states of many particles, then there is a lot to be destroyed. Okay, so if we consider even a pure state of n entangled qubits, then a central fact about quantum mechanics is that such a state, in general, requires something like 2 to the n parameters to fully specify it. Okay, I need one amplitude for every possible configuration of all n of the bits, right? Giving me a state like this one, which is a vector of exponential size. Okay, this of course is the central thing that makes quantum mechanics, seemingly difficult to simulate using classical computers, and is also the central fact that we hope to exploit by building quantum computers. From the perspective of someone trying to learn about a quantum state that they find in the wild or in nature, this shows up as a problem. Okay, this says that even if I want to learn a state approximately, forget about learning the amplitudes to infinite precision. Right? Even if I just want to learn them to some reasonable precision, still I need a number of copies of my state that grows exponentially with the number of qubits. Okay? Because of an additional fact, which is that if I measure a single copy of my n-qubit state, then even though in some sense there are 2 to the n bits there, any measurement is going to tell me at most n bits. Okay, this follows from a fundamental result proved in the 1970s, which we call Halevos theorem. Right? It basically says there's no way to use qubits to get a general purpose compression of classical information. Okay, if the sender and the receiver have pre-shared entanglement, then you can get a compression by a factor of 2. But no more than that. Okay, even in that case. So in some sense, quantum states have this exponentiality under the surface, and yet as soon as you measure, you collapse, and then it looks like it was only n bits all along. Okay, except that sometimes it looks like more than that because you can arrange interference, right? But it all depends on exactly what kind of question we're asking. Okay, so this raises almost a philosophical question. So should we say that these 2 to the n complex numbers, these amplitudes, are sort of really there in the first place in a single copy of psi, or are they just in our heads? Are they just a mathematical description that we use to calculate what we expect to see when we measure this object that really has size n? Okay, so apparently, the philosophy of quantum mechanics, this is what's known as the ontic versus epistemic debate. If you think that the amplitudes are really there, then that's the ontic view, and if you think that they're in your head, that's the epistemic view. Okay. I won't use such fancy words for the rest of this talk. Okay, the way I think about it is, we can get some intuition by just looking at the analogous question for classical probability distributions, right? If we had a classical distribution over n-bit strings, well, in some sense, that too involves an exponential number of parameters, right? In this case, probabilities. Okay, right, I have to specify a probability for every, for all 2 to the n of the strings. Okay, but there it seems pretty clear that, these probabilities are just, in our heads, right? They're something that as, Bayesians, as prediction agents, we may use to, predict which strings are more likely than others. But really, out there in the world, there's just n bits, right? And, you look and you see that it's, and once you look, then you know which n bits they are. Okay, so in the quantum case, we can't tell any story that's quite that simple because we know that interference is possible, and we know that in some cases we really do need to remember that this is a quantum state and it involves 2 to the n amplitudes. Okay, but the theme of this talk is going to be that in many of the cases that we care about, a quantum state can be shown, non-trivially, but it can be shown to act a lot like the classical probability distribution, in terms of how many copies of it you would need to learn something, in terms of how much information you can actually extract from it by making measurements. Okay, so before we go further, a very quick review. So for most of this talk, I'll be dealing with mixed states. Okay, a mixed state, is just one can think of it as just a probabilistic ensemble over pure states, and we represent it by a matrix like this. It's a convex combination of different rank 1 matrices like these, outer products of states of pure states with themselves. Okay, so in general, any mixed state in d dimensions is a d by d Hermitian positive semi-definite matrix with trace equal to 1. This should be familiar. Okay, it's the most general kind of state in quantum mechanics, and it encodes everything measurable about our mixture, right? If 2 different mixtures lead to the same density matrix, then they are operationally the same. Okay, and now we'll be interested in this talk mainly in measurements with just 2 outcomes. Okay, yes or no measurements. Okay, and the most general kind of measurement is what we call a 2-outcome POVM, positive operator value measure. Okay, and I'll just describe it as follows. That any 2-outcome POVM we can think of as just being represented by a d by d Hermitian positive semi-definite matrix. Okay, I'll call that matrix E. Okay, now its trace does not have to be 1. Okay, all we require is that all of the eigenvalues of E are between 0 and 1. Okay, for those who know, I'm thinking of E as just the accepting POVM element. Okay, and then the key rule is the following. Okay, if I apply the measurement E to the state rho, then it accepts with probability trace of E times rho, and it rejects with probability 1 minus trace E rho. Okay, so this will be the board rule for the purpose of this talk. And I haven't specified what happens to the state after the measurement, but I will say something about that later when that becomes important. Okay. Okay, so now let's discuss the problem of quantum state tomography. Okay, now this is a central problem in experimental many-body physics, and this is just this situation where you have a machine that can create a lot of copies of some unknown d-dimensional mixed state rho. Right? Every time you run the machine, it creates another copy of rho. Okay, and you would like to measure all of these copies, maybe measure each one separately, maybe even apply a collective measurement across many copies. But whatever you do, your goal is to produce an approximate classical description of rho. Right? You actually just want to learn the d by d matrix. Okay. Now, it was surprisingly recent that we actually learned what is the sample complexity of this task. That is, how many copies of rho are necessary and sufficient to learn rho tomographically. Okay, it was only a couple years ago that it was proved that maybe the first thing that you would guess is indeed the correct answer. Namely, you need about d squared copies. Right? Why would we expect d squared? Well, that's about the number of parameters that there are in a d by d density matrix that have to be learned. Right? So it's not that hard to see that you need at least d squared copies, but until recently it was only known how to do it using like d cubed copies. Okay, and very, very recently, in a breakthrough by these two groups independently, it was shown that you can do it using only about d squared copies, which is the information theoretic limit. Okay, so that's nice, but the problem is that we'll be thinking about entangled states of many particles. As I said before, where we think of d as exponential in the size of the system. Okay, so even linear in d would have been, completely infeasible, right? Very, very quickly. Okay, so this is well known to the experimentalists that tomography quickly becomes infeasible as the number of particles increases. Okay, and I think the world record for doing full tomography of an unknown quantum state was by the Innsbruck group about a decade ago, where they were able to learn the state of an 8-qubit trapped ion system. Okay, it took about 656,000 different measurement settings. I don't know how many students were involved in doing all the measurements, but it took them quite a while. Okay, and like to do for 10 qubits, forget it. Right, it's just not going to happen. Okay, I said for full tomography. Right now, of course, if you know something in advance about your state, like your state probably lies in this subspace, and you just have to confirm that or rule it out, then you can save a lot in the number of measurements. Okay, but we're talking about the completely general case where you don't know anything in advance about what your state might be. Okay, now another motivation for trying to understand this exponentiality of quantum states, besides tomography, is understanding these sort of skeptics who, for a long time, have been saying that quantum computing is never going to work. Right? It just it's just too absurd. It's not possible. I've shown, here are some of the prominent skeptics of quantum computing. Okay, now, the field of quantum computing, actually, when I was here at the Technion a couple months ago, I gave a talk about a different subject, which is about how within the next year or two, we may be in a position to actually experimentally refute these people. Okay, it looks like the groups at Google and IBM are very, very close to being able to solve some sampling task with using systems of about 50 qubits, which they're building and testing right now, which, as far as we know, should take about 2 to the 50th time to simulate classically.
They're skeptical about having a fault tolerant.
Well, okay, but Gil, I have right on my blog, on the record, saying you're not going to do this even with 50 qubits. So that, I think, of course, no matter what you do, someone can always say, okay, but you're not going to do the next thing, right? Gil has said, you're not going to do 50 qubits, okay? And I think that within the next year, that is likely to be falsified. I've tried to understand, sort of, okay, let's say we interpret their position to be, okay, maybe you can do it with 50, maybe you can even do it with 1,000, but, at some point it has to break down, right? So why do they think that it would have to break down at some point? Well, for many of them, the problem just seems to be that a quantum computer would manipulate an exponential amount of information using only a polynomial amount of resources, like time and space, and that feels to them like cheating. Okay. One response is just to say, well, this is what quantum mechanics seems to say. Quantum mechanics has passed every test for 100 years. Maybe it will fail the next time, but let's try it and see what happens. And, if it passes the test, well then, you'll just have to adjust your intuition to that, right? But I think that there's actually a different response one could give, which interests me a lot. And that's, we can question, in what sense is a quantum state really an exponential amount of information? Okay, because as we saw before, it's like it's only a certain Platonic view that sort of leads to this view that the quantum state is exponentially large, right? Once we ask the question more operationally about how much information can we actually extract from a state, then very often it looks like, much more reasonable. It looks like only a polynomial amount of information, but which is accessible to us in some ways that it wouldn't have been accessible classically. Okay, so that's sort of the theme of this talk. Can we tame the exponential beast? Okay, the idea being to sort of shrink quantum states down to a reasonable size by asking what they'll actually be used for. Okay, so now, I've had a long sequence of works motivated by this, where, I've tried to use tools from theoretical computer science, in particular from an area called computational learning theory, and often just take these tools very off the shelf and just apply them to reconstruction of quantum states and see what they give. Okay, and just to, so I'm going to talk mostly about one of these, which is, a very recent work in this direction, but just, to, but it builds on some of the earlier ones also. Okay, so just to give you a sense of sort of what has been done in this area, in 2004, I had what's called a post-selected learning theorem. I'm actually going to walk you through that in this talk because my new result builds on this earlier post-selected learning theorem. Then in 2006, I had something called the quantum Occam's razor theorem, okay, which is intended as sort of an alternative to quantum state tomography. And what this Occam's razor theorem said is, well, let's say that you have a probability distribution over two outcome measurements on a quantum state, right? Let's say on an n-qubit state, okay? Now, you don't have to know this distribution, okay? But now I'm going to tell you, you get a bunch of independent samples from this distribution. Okay, so repeatedly, someone picks a measurement at random from this distribution, and they tell you which measurement it is, and they also apply it some number of times to some unknown n-qubit state rho, which you're trying to learn, right? And they tell you approximately the expectation value of, the probability that this measurement accepts rho. Okay? Now the question is, how much data of that kind do you need before you can predict the behavior of rho on most further measurements drawn from the same distribution? Okay? So I'm not asking you to learn the density matrix of rho. You don't have to do that. Okay? We know that takes an exponential amount of data, but we're not asking you to do that. Okay? Just asking you predict the behavior of rho on most measurements drawn from this distribution. Okay? What I showed in 2006 is that if that's your goal, then you can do that using only a linear in n, linear in the number of qubits, amount of sample data. Okay? So you get an exponential improvement over what you would have needed for full quantum state tomography. Okay? Of course, you only achieve something weaker. I can't avoid that. Okay? But if in practice that's all you care about, learning the behavior of your state on most measurements with respect to any distribution you want, and the measurements are, have only a few outcomes each, you can do that with only linear and n data. Okay, I'm happy to report that just within the last couple months, an experimental group, quantum optics group in Rome, did the first experimental demonstration of this quantum Occam's razor theorem, and they used it to approximately learn a 6-qubit photonic state using a very small number of measurements. Right? The result of their experiment is that my theorem appears to be true. So, but it's nice to have experimental confirmation. Okay, and then by the way, I said it's linear. I didn't tell you what the I never worked out what the constants are. But when you do the experiment, you find that the constants are perfectly reasonable. This is perfectly doable in practice. Okay, so so I had I've been interested in sort of the power of quantum advice states in complexity theory, like a quantum state that someone would hand you to try to help you solve some computational problem. And can we sort of bound how much more powerful that can ever be than a classical advice string of a similar size? So we've had results about that. And then, with Elad Hazan and Jinyi Chen and Ashwin Nayak, we have a brand new result about which extends this quantum Occam's razor theorem to a setting called online learning. Where here there doesn't even have to be a distribution over measurements. The measurements can be chosen one by your worst enemy to try to trip you up, right? And this enemy can even know what everything you've done in the past, and use that against you. Okay, and even then, we can bound the number of mistakes that you're ever going to make in estimating a quantum state as basically just linear in the number of qubits. Okay, so that's online learning. If we have time at the end and you want to ask me about this or about this, I have some extra slides about it. But for the rest of this talk, I mostly want to tell you about this new result that I have, which I call the shadow tomography theorem. Okay? Questions? Okay, so let me give you sort of the a much earlier result that I'm going to build on for this shadow tomography theorem. This is something that I like to call the absent-minded advisor problem. Okay, so here's the situation. We have a PhD advisor who is both infinitely wise and infinitely benevolent, like most PhD advisors. Okay, but this advisor is also very absent-minded. Okay, and students come to him for advice, but he doesn't really remember what problem each student is working on.
Excuse me.
Okay, what?
What is the reasonable size?
Excuse me?
What is the reasonable size of a state?
Oh, well, yeah, that's exactly what we're going to address. That's exactly what we're going to talk about. Okay? So what the advisor would like to do is just hand out the same generic advice to all the students, and the student should be able to just adapt that advice to whatever is their particular problem. Okay? Now, we'll imagine that each thesis problem is an n-bit string, and then it has just a yes or no answer. Simplifying assumptions, spherical cow or whatever. Okay? And so now it's clear that the advisor could just hand every student an enormous lookup table, right, which would be a string of 2 to the n bits, and which would store the answer to every possible question. Okay? I forgot to say, all communication here is one way, from advisor to student. Okay? So the advisor never hears what's the student's problem, right? So the advisor could just hand a 2 to the n bit string that contains the answer to every problem. Okay? And our question is, could the advisor achieve a large compression by sending a quantum state to each student? Okay? So, could the advisor send a quantum state of, say, n squared qubits or something like that? Now, this is a little different from Halevo's theorem because we're not asking that a given student be able to learn the answer to every thesis problem, right? We're just asking that this student should be able to measure this state, this n squared qubit state, in such a way that they learn the answer to any one thesis problem of their choice, right? So that they learn one of these 2 to the n bits, of their choice. Okay, so now it was a non-trivial result in 1999 by Ambayanis, Nayak, Tashma, and Vazirani to say the answer is no. Okay, even for this more relaxed task, in fact, quantum encodings give you no real advantage at all over classical encodings, or at best sort of constant factor advantage. Okay, what they said is that actually in general, there's nothing better for the advisor to do than to send each student like 2 to the n qubits. Okay, so you could think of this as bad news that actually quantum communication does not help for a task where you might have hoped that it would help? You know, it's known that quantum communication can give you huge advantages, by the way, for other tasks. You know, we have examples where it does help a lot, but for this task, it doesn't. Okay? But these observations that I made in 2004 or so is that one can sort of turn this computational lemon into lemonade. Okay? One can extract something positive from it. Okay, and how do we do that? Well, let's imagine, you know, now that Alice is the advisor, Bob is the student. Okay? And let's say, you know, we just think of it as Alice wants to describe a d-dimensional mixed state row to Bob, well enough for Bob to not necessarily recover row, you know, as a matrix, but just to estimate trace of EI row to within an additive error epsilon for any of M two outcome measurements, E1 up to EM, which are known to both players. Okay? So in other words, you know, there's some list of M two outcome measurements that everyone knows, and the task is just for Alice to take this state that, you know, she knows a classical description of, right? And she has to somehow describe the state to Bob well enough that Bob can calculate trace of EI row for every I, or at least approximately. Okay? That's our problem. So, you know, clearly, you know, what are the trivial protocols for this problem? Well, Alice could always send Bob, you know, just a classical description of the whole density matrix rho. But if she does that, then she's sending about d squared bits. Okay? Alice could also send, she could just tell him for every I, here is what is trace of EI rho, approximately. If she does that, then she's sending Bob about m bits. Okay? We're interested in a situation where both D and M might be exponentially large. Alice and Bob might care about the behavior of an exponentially large state on exponentially many different two outcome measurements. Okay? And the interesting theorem is that even then, Alice can still get the information over to Bob that he wants by sending him only a polynomial number of classical bits. Okay? In particular, only this number, about log of m times log of d divided by epsilon cubed. And if you care enough, that epsilon cubed can become an epsilon squared. Okay. The way, you know, I'll show you in the next couple of slides a proof of this theorem that gives this bound here. Okay. And then we're going to use that for this more recent thing that I call shadow demography. Okay, so again, what we're saying is that if we think about our n-qubit state in terms of its behavior on all possible yes or no measurements, it seems like this astronomically large object. Okay, but if we restrict our attention to, you know, what is the behavior of psi on, let's say, you know, any set of measurements of merely exponential size. Like, for example, all measurements that could be performed by a quantum circuit with at most n squared gates, let's say, then psi shrinks to a much, much more manageable size. We can describe this information here using only about n cubed classical bits. That's what we're saying. Okay, so how does the theorem work? What is the protocol that achieves this? Okay, well, Alice is trying to describe the state rho to Bob over a classical channel. Okay, for technical reasons, she's actually trying to describe what we call an amplified version of rho. It just means many copies of rho. Okay, a tensor product of some number of copies of rho. Okay, so now initially Bob knows nothing about which state, right? The state could be anything. Okay, and we're going to model that by saying that Bob's initial hypothesis for what rho is the stupidest possible guess. What's the stupidest possible guess of a quantum state that you don't know? Well, the maximally mixed state. Okay? state whose density matrix is just the identity matrix divided by the dimension D. Right? We're actually divided by what I'll call D star, which is the dimension of this amplified Hilbert space. Okay. Now, what Alice is going to help Bob do is repeatedly improve his guess by telling him what are the identities of measurements in his list where his current guess would lead to a badly wrong answer. Okay, and then Alice will tell Bob for that measurement what should the answer be. And Bob can then use that information to improve his guess. Okay, so let's say his current guess after t iterations, is some state that we'll call rho sub t minus 1. Okay, then Alice will tell Bob, so it could, so there are two cases, right? It could be that whatever is Bob's current guess, it actually has approximately the same behavior as rho, the true state, on every measurement in the list, E1 up to En, right? If that's the case, then we can stop right now, right? Bob has a good enough guess, okay? We don't care if it's far from rho in trace distance, right? As long as it leads to the same behavior as rho on these M measurements, then we're happy. Okay? The second possibility is that there's some measurement on our list for which Bob's current hypothesis does not lead to an approximately right answer. In that case, Alice tells Bob the identity of such a measurement. And then Bob uses that information to improve. How does he improve? Well, he lets rho sub t, his next guess, be the state that's obtained by starting from his previous guess, rho sub t minus 1, and then performing the measurement where his current guess does badly, and then post-selecting on getting the right answer. Post-selecting just means we condition on, the event where Bob measures and he gets the answer that Alice said he should get for this measurement, right? And then we let rho sub t be like the state of his guess register, if that happened, right? Now, you might say post-selection is an unphysical process, right? If Bob actually had this rho t as a quantum state in a memory somewhere, then the chance that he would succeed on all these post-selection events might be very, very small. Okay, but we're not worried because Bob can just store a classical description of rho sub t in his classical computer, right? And then he can easily simulate the act of post-selection.
You're not worried about memory?
Yeah, let's say we will leave it to the future to worry about memory and computation time. Right now, we're just trying to prove what I promised you. Okay, that this can be done with a small amount of classical communication. Good. Okay, so his guess repeatedly improves. Now, by definition, in some sense, when and if this process ever stops, Bob must have a hypothesis that works, right? Because if he didn't, then we wouldn't have stopped, right? So whenever the procedure halts, we're done. Okay, so then, the only remaining question is like, how many iterations might it take until this procedure halts? Okay? So to answer that question, we need a very important interlude about a key concept in quantum measurement theory called gentle measurement. Okay, and this is about situations where you can measure a quantum state in a way that damages the quantum state only by very little, and which actually leaves the quantum state available for future use. Okay, so this goes by many names. It's, closely related things are studied under the name of weak measurement, and all the stuff that Yakira Haranov and his friends work on. Okay, but let me state a special case of this that will be all that we need for this talk. Okay, so here's a lemma. Suppose that we apply a measurement to a mixed state rho, and suppose that given knowledge of rho, we could predict that a certain outcome, like yes, will occur with high probability. say at least 1 minus epsilon. Okay? Then, this measurement can be implemented in a way that damages rho by very little. In the sense that after the measurement is applied, we can recover a post-measurement state, rho prime, whose trace distance from rho is at most square root of epsilon. Okay? This was proved by Andreas Winter in 1999. Called it the gentle measurement lemma. It's been independently rediscovered by other, I proved my own version of it, which I called the almost as good as new lemma. But they're all saying basically the same thing. Okay, the intuition is, if given knowledge of the measurement, I can almost perfectly predict the outcome, given knowledge of the state, I can almost perfectly predict the outcome of the measurement. Well, that only happens because I'm measuring in a basis where my state is already very close to one of the basis vectors, right? But if it's already very close to a basis vector, then it just almost certainly it just snaps to that basis vector, right? And the state is only damaged by a little bit. So in fact, something stronger is true. If you apply m such measurements in succession, even that only damages your state by something like m times square root of epsilon, at most that. And in fact, all the measurements, will accept with at least this probability. Which, if epsilon is much less than 1 over m squared, then this is non-trivial. Okay? And we can combine this gentle measurement with amplification. That is, with applying a measurement to many copies of our state, and then, accepting if and only if the majority of the measurement outcomes accept. Right? And then if epsilon started out small, then that will push epsilon down to be really, really small. Like if I do a majority among k copies, then that will push my error probability down to be 1 over exponential in k, just by a standard binomial theorem. Okay? So using these tools, I can now tell you what's the crucial claim about this post-selected learning procedure. Okay? And the key claim is that Bob will converge to a state, say rho sub big T, that behaves like the true state that he's trying to learn, rho star, on all the measurements in his list, after a number of measurements, or a number of iterations, that is at most logarithmic in the dimension of the Hilbert space. Okay? Why is this? Well, a very simple proof is just to look at the probability that the first T post-selection steps would all succeed if Bob were to start from the maximally mixed state, right? And then just apply the normal quantum measurements, without any magic powers. Right, and then we can so let's let P sub T be that probability, and then we can sort of bound it on both sides. In one direction, P sub T is at least, let's say, 0.9 divided by the Hilbert space dimension. Why? Well, because the maximally mixed state sort of contains every other state inside of it, in some sense. You can decompose the maximally mixed state as a convex combination of sort of any other state you want, like let's say the true state, rho star, plus something else. Okay, and now we can use linearity and say, well, look, if we had started with the true state, then we know that all the post-selections would have succeeded, right? Because the true state leads to the right answers for everything. Okay, and furthermore, by this gentle measurement lemma and amplification that I told you about before, the true state would not even be damaged by very much by each measurement. So we could keep reusing it over and over. And we'll just win every time. So let's say we lose with at most 10% probability, then our success probability is at least 90%, which means that our success probability, even on the maximally mixed state, was at least 90% divided by the dimension. Because, the maximally mixed state had, the truth as at least a 1 over d large component. Okay? But on the other hand, P sub T is also at most 2/3 to the number of iterations. Why? Because the way that this procedure worked, we only ever picked a new measurement because even conditioned on having succeeded on all the previous measurements, we still fail with high probability on the next measurement, right? So the probability that I succeed on each of the first t measurements has to decrease exponentially with t.
I have a question.
Yeah.
How many states row of t are there?
The number of states in the total Hilbert space is going to be like exponential in d, right? So really a lot. Okay, you know, the number of bits needed to fully describe such a state is like d squared. Okay, this is why it's surprising that this procedure terminates after only about log of d iterations.
But how many row t's would give the right answer? How many possible good rows?
How many possible good ones? There might be many good ones. You know, the theorem is not telling you how many. There might be a very, very large space of possible good ones. Or it might be only a small space, you know, that both are possible.
So is Alice transmitting information? She's doing
Yeah, she is, yes, she is transmitting information. I am bounding how much information she needs to transmit. I am telling you that it is exponentially less information than you might have feared.
Right, but is this way that she's transmitting it?
Yeah.
Do you know what's the best way?
Oh, well, no, I can actually prove lower bounds that show that my procedure is very close to asymptotically optimal. Okay? Which means, you know, you can improve in the lower order terms, you can improve in the constant factor, but for the problem I'm solving, I can show that this procedure is pretty close to optimal. You know, in the computer scientist sense of, you know, if it's within a factor of 100, I call that pretty close. Okay? I don't care about constants. Okay? I care about the dependence on m and d. Okay? So just solving these inequalities, we find that t, you know, this thing has to stop when t is, you know, more than log of d star. Okay? Which means it's enough for Alice to tell Bob about, you know, let's say about log of d measurements. Telling him about each one takes about log of m bits, because she has to specify which measurement in the list. So you get log of m times log of d. That's basically what's going on here. Okay, now, you know, I originally proved this in order to prove something about complexity classes, specifically about the power of these quantum advice states that I mentioned before. I could show that anything you can do efficiently on a quantum computer, that's this complexity class, BQP, bounded error quantum polynomial time. This says with polynomial size quantum advice. And this says that any such thing could be simulated in polynomial time on a quantum computer using polynomial size classical advice plus the ability to post-select on measurement outcomes. Okay, which, you know, so you know, a priori quantum advice could have been infinitely powerful, right? Could have let you solve NP-complete problems, could have let you solve the halting problem. Okay, this puts the first ceiling on the power of quantum advice that we've known. It is, you know, one of my favorite open problems in quantum computing theory is this one. Can quantum advice always be simulated by classical advice without needing post-selection? Okay, but this shows that at least you can do it with post-selection. Okay, so now let me tell you what is the new result that I have. Okay, and this is what I call shadow tomography. Originally, I was calling it batch tomography, but, you know, then I talked to a physicist friend, Steve Lamea, who said, you know, I should call it something that sounds sexier. You know, and so basically the idea is that this is like tomography, except that we're not going to learn the density matrix of a state. We're just going to learn the shadow cast by the state on a bunch of measurements that we might care about. Okay, so let me state for you the theorem. Okay, it says, let rho, again, be an unknown d-dimensional mixed state. And now suppose we have a list of known two-outcome measurements, say E1 up to EM. Okay? And suppose that we want to know a trace of EI rho to within an additive error of epsilon for every I in our list. Okay? Then it says that there is some measurement that will tell you that, with high probability, and it measures only this number of copies of rho, this number here. Log to the 4th m times log of d over epsilon to the 5th. Okay. So, so I should say, for this task, right? Once again, it's pretty easy to do this with about m copies of rho, because all I would have to do is just measure, measure some copies to learn E1, measure some other copies to learn E2, and so forth. Right, just measure separate copies for each EI. Okay, it's also, by the 2016 results on tomography, we know that we could do this using d² copies of rho, because then we just do ordinary tomography. We learn the density matrix of rho, and then we know anything we want about it. Okay, so again, the surprising part is that I can, even if m and d are exponential, I can do this using a polynomial number of copies of rho. Okay, using a number of copies which is polynomial only in log d and log m, and 1 over epsilon. Okay. Now, I certainly don't know that if this is optimal. It's pretty large in practice, as you can see. I should mention very within the last month. Some colleagues have improved this epsilon to the 5 to epsilon to the 4. I think it should probably be epsilon to the 2. I think, this log to the 4th m, that should probably be only log of m or so. And this log of d, I don't even know if that has to be there at all. Okay, that might just be an artifact of my proof. Okay, but for this to to be doable, I raised as an open question 2 years ago whether this can even be done at all, right? And I was on the fence. I thought maybe that this I could just rule out that anything like this could be done. I tried to prove it impossible. I couldn't prove that. Now I know why I couldn't prove it impossible. Okay. So what's the challenge here? The challenge, of course, is you get only a few copies of rho, and way fewer than m copies, and somehow you have to learn rho's behavior on all m of these different measurements, yet without destroying your copies of rho in the process. Okay, so the intuition. Let me just quickly tell you the intuition behind this result. Okay, it's a lot like the situation that I showed you before. It's a lot like that post-selected learning theorem, except that in this case there's no Alice. Okay, there's no Alice, to tell us, oh, here are some measurements that would be useful to condition on, right? That will give you, useful, that will help you converge toward the behavior of the true state, right? So in this, here there's only a Bob. And Bob has some copies of rho. So if we want to, so we can try to do this thing of repeatedly finding a useful measurement to condition on, and then conditioning on that measurement. But, in this case, Bob will have to find the useful measurements himself. There's no one there to tell him. Okay? So in order for Bob to find the useful measurements himself, we have to use another recent tool, which is called the quantum OR bound. Okay? Now, this quantum OR bound is something that I claim to have a proof of in 2006. Okay? So here's what the quantum OR bound says. It says, if I have an unknown mixed state, I have some known 2-outcome measurements, and let's say I'm just trying to distinguish 2 different cases. Case 1 is that there is some measurement in my list that accepts rho with high probability, and case 2 is that no measurement in my list accepts rho with high probability. And I have some gap of epsilon between the 2 cases, right? Then the OR bound says I can make a measurement, that distinguishes these 2 cases using only about log m over epsilon squared copies of rho. Okay, so I claimed to show this in 2006. In 2016, Aram Harrow, Cedric Lin, and Ashley Montanaro, well, discovered an error in my proof. But fortunately, this is the best kind of error discovery. They also fixed it. Okay, they gave a correct protocol that achieved the same bound that I claimed. It remains open whether my original protocol also worked. What we know is that the proof that my original protocol worked was wrong. Okay, so they use some kind of they apply a bunch of measurements, the EIs, they simulate applying them, but only conditional on a control qubit being in the state 1. And then they sort of periodically measure the control qubit in like a plus-minus basis to see if the control qubit is decohered. And the idea is that if a lot of these measurements are like leading to accepting, then that's going to decohere the control qubit, and I'll notice it, and then I'll know which case I'm in. That's sort of the idea. You can look at their paper for details. And so then I sort of bootstrapped their result to get a procedure that not only tells you, is there a measurement that accepts in the list that accepts your state with high probability, but if there is one, then it actually finds such a measurement. Okay? I used a very, very common trick for taking a decision procedure and turning it into a search procedure, which is binary search. Right? You just ask, is there such a measurement in the first half of my list? If there is, then I recurse look at the first quarter of the list, second quarter of the list. If there's no such measurement in the first half of my list, then I look in the second half of the list. And if it's there, then I recurse in the second half of the list. Right? This is where I get this blow up to log to the 4th power of m. And you have to be very, very careful in how you do this to avoid buildup of error. Okay, but whatever. And then basically I'm just putting together all of these ingredients to get this shadow tomography theorem. Okay, so this is just my second last slide. The implications of shadow tomography. Here's a kind of striking implication, okay, of what we've proved. Given an n-qubit state, say psi, for any fixed polynomial p, by measuring only polynomial in n number of copies of your state, you can learn that state's behavior on every quantum circuit with at most a polynomial number of gates. Right? This is just applying my shadow tomography theorem, using the fact that there are at most exponentially many different quantum circuits of at most a polynomial size. As long as we fix a finite basis of gates. Okay? Another implication is that if you want a scheme for quantum copy-protected software, that is, like a quantum state that you could use to compute some function, but you can't use to create more states to let you compute the same function, which is a problem I've been interested in for more than a decade. Well, if you want this, then it has to depend on some computational assumption. Right? Information theoretically, if I give you polynomially many copies of a quantum program, or you buy them at the store, well then there is some measurement that you can make that will tell you the behavior of that quantum state on all 2 to the n possible inputs. Right? Shadow tomography assures you of that. Okay? Likewise for quantum money. We can say that any possible scheme for quantum money, well, you need either a computational assumption, or else the bank has to maintain an enormous amount of secret information, which was the case in Stephen Wiesner's original scheme for quantum money. Okay, but if you have neither of those two, then a counterfeiter who had unlimited computation time could always, by measuring a polynomial number of legitimate quantum bills, they could always learn the behavior of the bill on every possible verification test, and that would then let them mint new bills. Okay? This again follows almost immediately from the shadow tomography theorem. Okay, so summary. The tools of computational learning theory let us show that often the exponentiality of quantum states is more bark than bite, i.e. there's a short classical string that specifies how your quantum state behaves on any yes or no measurement that you could actually perform. Okay? There are applications of this from complexity theory to experimental quantum state tomography. I hope more applications will be discovered. Unfortunately, these results do not generalize to measurements with, say, exponentially many different outcomes, nor do they generalize to learning an unknown quantum process. And one can prove that they don't generalize in those cases, because one can give lower bounds, says that these results just don't hold in those cases. For me, the biggest future challenge is to find subclasses of states and measurements for which this kind of learning can be done not only with a small number of copies, but also with a small amount of computation. And I should mention that there is some very exciting recent progress on this by Fernando Brandao et al. And so they have already improved my shadow tomography procedure so that it's more efficient computationally. For example, while my procedure used an amount of time to implement this, linear in m, the number of measurements, theirs uses only about square root of m. Okay? And mine also used like d to the log d computation time, d being the Hilbert space dimension, and theirs uses only polynomial in d computation time. Okay, but I think if you make more assumptions on your quantum state or on what your measurements are, then it should be possible to get procedures that are even practical to implement computationally. So let me stop there. Thanks. Yeah.
Do you think that shadow tomography has implications for quantum foundations in the sense that perhaps the quantum universe is related by underlying classical universe some finite epsilon polynomial even?
Well, okay. I think I would love it if this result had some kind of foundational implications, but I do think that you have to look carefully at what the result says and doesn't say. Right? So, nothing in this result rules out, says anything against quantum computers giving us exponential speedups. Right? It says nothing against Shor's algorithm or anything like that. Right? So you still have all of that to deal with. And furthermore, nothing in this result says anything against even, it being possible to get exponential savings using quantum communication for certain tasks. Okay, and in fact, we know that's possible. There's a famous result of Ron Ross from 1999 that says there is some communication problem that Alice and Bob can solve by exchanging exponentially fewer qubits than the number of classical bits that they would have to exchange. Right? Now, why is that result compatible with my results? Well, if you think about it, right, it's because of this dependence on m. Basically, right? So basically what my results imply is that as long as Bob's input is very small, like let's say it's only log of n bits or something, then quantum communication can give you only a small savings over classical communication, right? And this absent-minded advisor problem, where the student's input is small, right, is a good example of that. Okay, in Raz's problem, where he achieves the exponential separation, not surprisingly, Bob's input is large, right? My result, well, my post-selected learning theorem showed that that was a necessary feature of Raz's example, right? But but if you're willing to consider cases where Bob has a large input, then we know, yeah, quantum states can give you exponential compression there, right? Now another thing to keep in mind, right, is that, we know that if you needed to do full tomography, then you would need exponentially many copies of the state, for that, right? Yeah, well,
on the measurements that you can make.
Yeah, well, most measurements will take exponential time to implement, right, which suggests that if you could only do it for very small, you could only apply them for very small Hilbert space dimensions. Right, but then there's a notion, if you want to get into this further, that's called tomographically complete sets of measurements. Right? So they're actually pretty easy to apply sets of measurement bases, such that if you knew the behavior of your state on every measurement, in this set, then from that alone, you could reconstruct the entire density matrix, right? That's what it means to have a tomographically complete set. And now some people have pointed out to me, well, Scott, there are tomographically complete sets of size, D or D squared or something. So why does that not contradict your theorem, right? Because, my theorem shows that it's possible to do, it's possible to learn the behavior of a quantum state with only this number of measurements, right? And if if m is like d squared, then this is still, polylogarithmic in d, right? And then that's saying we could do quantum state tomography with only polylog of d measurements, which we know is impossible. So how do we resolve that paradox, right? Well, the resolution involves epsilon, okay? It involves the fact that if you wanted to really learn your full state by a tomographically complete measurement, then you need epsilon to be like 1 over d. And then that's what kills you here, right? So then my theorem just tells you again that, yeah, you can do tomography using polynomial in d copies of rho, which you already knew, by other ways.
Okay, let's think, we're short on time, so let's thank Scott again.
All right.